So I have started to record the class. So the class on 18 November. Good morning. So last class we were discussing about the solution of the problem in abacus. So this is what we have done in the last class. So we assume C is equal to, in the problem we assume C is equal to 1, A is equal to 1, L is equal to 1, E is equal to 1. So the problem which we have a bar element where there is a loading, and the loading is given by Q is equal to Cx. So this is the analytical result which we are going to get. We divide it into 3 elements. So this is my first node, second node, third node, fourth node, and U1 is equal to 0, U1 is equal to 0, and this corresponding to U2, U3, U4. So when you look at the analytical expression, so we found out that the displacement at node 2 is equal to 4.33, displacement at node 3 is equal to 7.67, and displacement at node 4 is equal to 9. So this is what we got from the analytical expression, and this is the result from your FEM formulation. So you got 4.33 on node 2, 7.67 on node 3, and node 4 you got 9. Then we did the same problem in abacus. So we got it like this: 4.25 at node 2, 7.5 at node 3, and sorry, it is actually 8.75. 8.75 at node 4. So this is the result which you got from the last class. So we found out that the FEM formulation, in the FEM formulation you have taken 3 elements, and here also in the FEM formulation we have discretized into 3 elements in abacus. So this is the result from abacus. So we got it that there is a variation in the, there is a variation between our result and abacus result. Then in abacus we have increased the element size, increase the number of not element size, we decrease the element size. So we increase the number of elements. So we increase from 3 to 30. We increase the number of element to 10 times 30. So then the result I got, it is 4.33. Then here I am getting 7.665, and here I am getting 8.9975. So you see that whenever I am increasing the number of elements, the results are matching with the result which we got from the analytical result. So then what we have done that initially we have been, in the last few classes we were talking that these two systems are equivalent. When I am deriving the finite element formulation of this problem, we got it a condition like this. So that means the problem here I have applied only the forces only at the node, and this is a continuous loading condition. So these two problems which we found equivalent. So that means the result which I got from here should be able to get if I use the nodal load here. So what is a nodal load? So what is a nodal load? On node 1 we have applied 0.161, and node 2 I am applying 1, and node 3 I am applying 2, and node 4 I am applying 8.6. So you are getting 1.333. So that means if I apply this problem is equivalent to this problem. So that is so we will, next what we are going to do, we will solve this problem in abacus, where we are going to, instead of applying a distributed load dikes, we will apply the nodal point and see the result in abacus. So that is what we are going to do. So remember that node 1 we are applying 0.16, and node 2 I am applying 1, and node 3 I am applying 2, and node 4 I am applying 1.333. So these are the node 2 will be applied in abacus, and we see the result. So we will see the result. Okay, so I hope you.
Okay, so I hope you.
So I hope you are able to see the screen now. So we will delete this. We have created a node which is analytic. We will delete that one. What we are going here. So let's say we can delete this one. So we will delete this load. We will upload as per. So what we are concentrated force. So concentrated force on the first node. This is a node 1. So node 1, in strictly speaking, you don't need to apply any node because node 1 does not matter actually. So we need to apply 0.1666. On node 1 we have to apply. Then on node 2 we will apply another concentrated load. So here on node 2, and the magnitude is equal to 1. And then on node 3, we are going to apply a concentrated force where the magnitude of the force is equal to 2. So the magnitude which I am going to apply on node 2 is equal to 2. And then node 4, I will apply a concentrated load that is equal to 8 by 6. Okay, so I am going to apply 8 by 6 is equal to 1.3333. So I am applying like this. So instead of applying a distributed load over the entire geometry, I will apply the equivalent load. The equivalent load, since we have divided into the 3 elements, 4 nodes. So we will apply the nodal forces, which we derived from our finite element formulation. So if you look at our finite element formulation, the nodal load has to be applied on node 1, that is equal to 1 by 6. And node 2, I have to apply a load of 1 unit. And node 3, I have to apply a load of 2 unit. And node 4, I have to apply a load of 8 by 6, that is equal to 1.3. So this nodal force we are applying in abacus. Then we will see what is the result which is given by abacus. So we will submit it. Just submit it. So it is completed. So we will look at the result. So we will look at the result. The result which you are looking is U1. So just so we will see. So if I am applying on not element node. So if I am looking on node 4, you can see I am getting 8.9999. So node 3, I am going to get 7.6666. And node 2, I am going to get 4.33. So these are the result I am going to get. Node 2, I am getting 4.3333. Then node 3, I am going to get 7.6666. And node 4, I am getting 8.999. So this is the result which you got when you apply the nodal load. So we come back to the PPT. So if we come back to the so you look at here. So when you apply the nodal load, so what we did actually, so initially, this was a problem which we have done in the last class. So this solved in abacus. So So we have continuous load Q is equal to Cx. So we divide it into 3 elements: first node, second node, third node, fourth node. So then we are getting in abacus U2, U3, U4. U4 I am getting 8.75. U3, what is the value I am getting? 7.5. Then this is I am getting 4.25. Case 1, we done it in abacus. Second case, what we did in abacus. So instead of applying a continuous load, what we did, so we apply a nodal load. This is equal to 0.166. And on node 2, I am applying a force of 1 unit. And in node 3, I am applying a force of 2 unit. On node 4, I am applying a force of 8 by 6, that is equal to 1.333. Then I am getting U2 is equal to 4.33. U3 is equal to 7.67. And U4, I am going to get 9. So this is the result. So speaking, it is not what is abacus shows. So maybe I will write what is abacus shows strictly. So it is showing 7.666. 7.6666, and this is 8.9999. Okay, so when you do the problem like this, you are going to get like this. So what is the difference actually? So this is the nodal load. You are going to get 7.6, 4.33, 7.666, that is equal to 7.67, and 8.999, that is equal to 9. So now if you look at, so these results are matching. These results are matching, but these results are not matching. So what may be the reason? So one thing you the last tutorial. So what I gave to you. So if you look at just a second. So this is the first element and second element. So what we have done here. So if you look at, this is a total load. Total load. I hope you remember this one. The total load is CL square by 2. And when you add the loads on the 2 node, you are going to get CL square by 2. So what we did here, not in the last class, previous classes, we wrote the first element condition like this. We found that it is equivalent to, this is actually a nodal load, this is equivalent to this condition. So that means the load is distributed. So even if you take the total load is actually the same. But if you look at the total load acting on the system is CL square by 2. Total load is actually acting, it is CL square by 2. And this is distributed to first node and this is distributed to second node. If you look at the magnitude which is distributed in the first node, it is equal to CL square by 6. And what is it is applied on the next node, node 2, it is applying CL square by 3. So if you look at, the load is not distributed equally on both nodes. So what is the percentage here? This, if you look at here, this is around 33%, and this is around 66.7. This is around 33.3 and 66%. That means whenever you have some loading on the things, so some loading, so let's say this is the loading is, the total loading is, let's say F. That means whenever you have like Q is equal to this uniformly distributed load, it's not uniformly distributed, it is in with respect to X. Then 30% is distributed in the first node and not 33.3% is distributed on the first node, and the 66.7% is distributed on the second node. The same thing you can see in the second element also. Second element, what is the total force? Total force is equal to 3 CL square by 2. And what is the load distributed on the first node? If you look at the first node, that means the second node here, second node, and this is the third node. That corresponding to the second node of the element. And if this is actually 4 CL square by 6. And this is equal to 5 CL square by 6. So now can you calculate how much percentage is distributed here? So if you look at here, how much percentage is distributed here? And how much percentage is distributed here? So it will be that much itself, 33% in one node and 66% in the other node. So what, it's not exactly 33% because you have, if you look at a triangular load, so this will be distributed. This triangle will be distributed 33.3% here and the 66.7 on the other node. And this rectangular node here, rectangular loading, which is applying 50% here and 50% here. So that will be the sum of that one. Okay. So that is what you need to understand. So the conclusion is, I will just tell you the conclusion. So if you have like a triangular loading, so let's say you have a triangular loading. So this is my first node and this is my second node. So let's say Q is equal to Cx. So here the loading is equal to 0 and here the loading is equal to Cl. So then if you, let's say total load is equal to the area of the triangle, that is equal to half of CL square. So let's say F, that is, let's say if I am representing F, in case of a triangular load condition, the first node, we can convert it into the nodal load by just applying 33.3% on first node F and 66.6% F on the second node. This is how the load distribution is going to come whenever you apply a distributed load, which is actually the distributed load, which is this magnitude is increasing. It's like a triangular shape. So I hope you are getting it. So whenever you have a triangular load from finite element, our finite element formulation, we understood that 33% is distributed on the first node and 66% is distributed on the second node. Now look at, instead of applying this one, let's say in the last tutorial, the last class, what we did, the last class I gave you a problem where Q is equal to constant. So where Q is equal to constant. So what is the condition if Q is equal to constant? Then the loading is like this, like a rectangular things. The loading is like this. So now if you look at first node and second load, let's say total force is maybe F dash, total force is F dash, then in this condition, 50% will be distributed to F dash here and 50% of F dash will be distributed to node 2. So if you look at the last tutorial and if you get the correct answer for that one, and if you look at the condition, if you look at the condition of the finite element formulation, you will see that if you take the total force acting on the element, that force is equally distributed on the first node and that is distributed in the second node. But that is not the case of in the triangular load. In case of triangular load, 33% will be distributed on the first node and 66.6 will be distributed on the other case. And if you have some exponential type loading, let's say I'm talking like this. This is my first node and this is my second node. Q is equal to, let's say, some constant into e raised to x. Then also you have to derive it and you have to find out, let's say this is maybe F double dash, what is some percentage, even I do not know now. We have to do the formulation. Some percentage will be distributed on the first node and some percentage will be distributed on the second node. What is your conclusion? Depending on the load intensity which is on the element, the load distributed to the nodal load will be different. If you have a constant distribution, that means uniformly applied load, uniform distribution of the force, then definitely 50% will be distributed on the first node and the remaining 50% will be distributed on the second node. But whenever you have a triangular load distribution, the loading, it's not a uniform distribution. The intensity of the loading is changing with respect to x. It is proportional to x. That means it's a triangular distribution, linear variation of the load. Then you will see that 33% will be distributed on the first node and the remaining the remaining 66.6% will be distributed on the other node. Like that, you can see different types of configuration. You can have, this is a linear combination. In the uniformly distributed mode means Q is equal to constant. So let's say uniformly distributed means Q is equal to constant. This is uniformly distributed load. And Q is equal to Cx means you have a triangular load. Like that, you can consider C is equal to X square. You have a parabolic loading condition. And Q is equal to C into e raised to X. You have an exponential loading condition. So there are different types of condition you can consider. And each condition, you will see that distribution of the load on first node and the second node will be different. But remember that if you have a Q is equal to constant, if Q is equal to constant, the load will be distributed equally on first node and equally on second node. I hope you are getting it. So that is how the nodal loads are derived from your FEM formulation. From the FEM formulation, whenever you have a continuous load application, when you formulate the FEM, what are you going to get? This continuous load will be converted into some nodal loads. That is what we are going to do. The continuous load will be converted into some nodal loads. Okay, so that is what is here. So I'm just erasing this one. Okay, so this is the distributor. That is why we can call it as this is an equivalent condition. So we have a continuous load that will be distributed to nodal loads. So that we have a continuous loading. It can be uniformly distributed load, or it's like a triangular load, or it's an exponential variation, or it's a parabolic variation. So in each case, you are able to make a FEM formulation such that while doing the FEM formulation, that will be this distributed load will be converted into the nodal loads, corresponding nodal load. But remember that the distribution of the load in both nodes will be different depending on your condition, whether it is constant, parabolic, exponential, like that, it will be different. So now we will do another case. We just need to check why the abacus is showing a different result in our case when you apply a distributed load. So what we are going to do, instead of dividing, so in our formulation, what we did in our formulation, the 33% is distributed in one node and remaining 66% is distributed in other node. So what we do here, so we assume a condition of equal nodal loads. So we understood that total load on the first element is CL square by 2. That I have divided equally in both nodes. So that means 0.5 CL square by 2. So that means if C and L everything is 1, then I can apply. If I am applying equally on both nodes, then it is 0.25 on first node, 0.25 on second node. Now if you look at the second node, the total force is 1.5. If C is equal to 1, L is equal to 1. Then this 1.5 I am distributing equally to both elements. Suppose I am considering a condition 0.75, 0.75. Now if you look at the third node, it is 5 CL square by 2. It is 2.5. If C is equal to 1, L is equal to 1. So this 2.5 load, I am dividing it into equally on both nodes, 1.25 and 1.25. So now, so you just add it in first node and second node. This is my first element. First element, if you consider 0.25 on both nodes. So you have 0.25 and 0.5. And now we refer the second element 0.75 on second node and 0.75 on third node. So I am just adding 0.75 and 0.75 on second node and third node. And if you look at the third element, 1.25 on node 3 and 1.25 on node 4. So I am adding 1.25 here and 1.25 here. So then you are going to get 0.25 on first node, 1 on second node, 2 on third node, and 1.25 on fourth node. We will try this one in abacus and we will see the result. So we will see the result. So let's say we come back here, then we go to the load. We delete the entire load. We will just change it. So first node, what is the force? The first node we have to apply 0.25. That is the force which will be acting on the first node. And now if you look at the second node, I am just reducing the node. Second node, instead of 1, I think it is 1 itself. It is 1 itself. Yeah? It is equal to 1 itself. So I am applying 1. And third node, if you look at the third node, it is equal to 2 itself. Somebody asked some question. Sir, we are unable to see your screen. Oh, sorry. I did not share that one. Yeah. Okay, now I hope you are able to see the screen. Okay, so in Abacus, what I am going to do, in each node, I am going to apply the force which is derived if it is equally divided on node. So first node, what is the force? First node, it is 0.25. I have already applied. Then second node, I am just editing that one. Second node, it is 1. And third node, what is the force to be applied? Third node, we are applying 2. And what is the force to be applied on fourth node? In fourth node, we are going to apply a force of 1.25. That is what we got. Okay, so we just apply this condition and we will see the result. We just see what is the result. So just submit it. So we will see the result. So you will see some very interesting result. So if you look at the displacement, so you will see that. So we are looking on third. You see fourth node, it is 8.75. And third node, it is 7.5. And second node, it is 4.25. So second node, it is 4.25. Third node, it is 7.5. And fourth node, it is 8.75. So come back here. So come back here. Yeah, this. So what is happening when you apply equal nodal loads? When you distribute the nodal loads equally, when you distribute the nodal, you are going to get 4.25, 7.5, 4.25. So you see the results are matching with the. So I will just erase this one for clarity. Now you look at in Abacus. So this is actually this is 8.75. So this is with continuous loading. With continuous loading. And this is with equal load. You see these two results are matching now. Okay, so when you apply the nodal loads, you see this is matching. This is matching. And when you increase number of elements to 30, the results are coming closer to here. So can you tell me what is your conclusion from here? Why the results are varying? Why there is a variation between these two results? If you look at these two results, why there is a variation from our FEM formulation and Abacus when you apply continuous load 3 elements with 3 elements. Now are you able to identify that why there is a variation? Can you just tell me the reason for this variation? Can you just type the reason for variation? So this is 1, 2. So you are getting U2 is equal to 4.25. U3 is equal to 7. It is U4 is equal to 8.75. It is here 7.5. abacus is equally distributing the load to the nodes of an element. Yes. So Manas has commented that abacus is equally distributing the load. So that means when you apply in abacus, what is happening that when you apply in abacus is actually distributing equally, irrespective of your loading condition. Even though you are applying a triangular load on the element, on the domain, even though you are applying a triangular load on the element, what abacus is going to do, abacus is going to distribute this load equally on the elements, irrespective of your loading condition. So what may be the reason why abacus is doing? Abacus, what may be the reason abacus did the coding like that? It's all with the coding behind. So what may be the reason abacus programmed like that condition? Can you just tell me what may be the reason behind it? Can you guess the reason? Irrespective, whether you apply a triangular load, whether you are applying a parabolic load, whether you are applying a exponential load, abacus what basically do, if you apply a continuous load, abacus will divide it into equally into both elements. But if you do the finite element formulation, you will get different result for different things. Whether you do with the one element, whether you do with the constant q is equal to constant, whether you do with q is equal to cx, whether you do with q is equal to cx square, whether you do with q is equal to f c into epsilon x, whatever be the variation you provide, you will have a different nodal load. Each case you will have a different nodal load. So Aslam has commented that only condition that nodes are programmed in abacus. So the condition that this loading is actually, the loading is basically, it is your choice. You any choice. I can apply a uniformly distributed load. I can apply a triangular load. I can apply quadrilateral cubical loading, then exponential loading. So I have infinite number of choice with my hand. So if abacus is trying to divide it into this element, they have to do the programming is difficult. They have to forecast your condition in each case, and they have to program it behind like that. So the possible way to avoid that one, they will just do only for this condition. Uniformly loading only they will do. So what is the advantage of that one? So they don't need to take effort in other that one. What is the advantage? What will be the things if you look at? So you see the condition you see if you look at 30 elements. So when you divide it into a abacus 30 element, so you see this is our matching. So what is your conclusion? So in a bar, what are your loading conditions? Suppose you have a loading condition like this. So this is your Q. Q is equal to some function of X. But when your element size is so small, so when you are decreasing the element, let's say your element size is so small, let's say element is delta X, when it is so small, what is going to happen that the loading onto that element, the difference between what is the condition, whether it is Q is equal to constant or whether it is equal to Q is equal to Cx, Q is equal to e raised to x, Q is equal to x square. So whatever be the loading condition, you will see that the variation is something like this. But when you take your element size much smaller, the difference between these two elements will be much smaller. The difference between these two nodes will be much smaller. So that is the reason, increase the number of elements from 3 to 30, then you are getting analytical result getting closer. So whatever be the variation, so means it's like whatever be the variation, when you divide a delta x, when delta x is actually tending to 0, so when delta x is tending to 0, what is going to happen? On that element, you will see that it's almost a uniformly distributed load. Are you getting? So when your element size is so small, when you're reducing the element size, even though your loading have a big variation, when you're reducing the element size, you will see that inside the element, you can approximately consider as the loading is uniform. So this delta x tend to 0 is actually, it's not, theoretically it is not correct. Finite element method, you have always finite dimension for the things. So delta x tend to 0, it's no is a wrong word I have used it. So but when delta x is small, the element size is small. When the element size is small, what is going to happen? So what will be the variation? Whether it is q is equal to cx, whether it is equal to x square, what will be the variation? You will see that inside an element, it is almost like a uniformly distributed load. So when you increase the number of elements, you are going to get approximately equal to the analytical solution. Okay, I hope it is clear. If you have any doubt, you can tell. Otherwise, we will go to tutorial. So that is a so that even you can have such condition, you can do the solution, even if you do the programming only like this. I think that is the reason why Abacus is in our program always distribute load equally on both elements rather than distribute unequally with respect to the loading condition. So you have any doubt? Or something is not clear, or you can tell. Okay, I hope nobody have doubt. And if we take constant load, then also there will be variation in Abacus. If you take a constant load, there will be no. If you take a constant load, you will get exact solution. You will get exact solution that you can check it. So you will not have variation. If Q is equal to constant, so this Q is equal to constant. So let's say suppose you have a condition like uh, suppose you have a condition like Q equal to constant. If Q is equal to constant, so this is equal to Q is equal to constant. Then you divide it into number of element, 3 element, first element, second element, 3 element. Then you will see that these results will be matching. These two results will match. Result will match. Whenever you have a variation like a triangular or a triangular load or parabolic load or exponential load, then only these two results will not match. But if Q is equal to constant, then your result will match in Abacus. That even you can verify it. The result has to match. So these two results will have no variation. You will get exactly what you derived in FEM formulation and what you did it in Abacus. Both will exactly match. Okay, I hope it is clear, Shaikh. Okay, so if you have any question, then otherwise we will go to tutorial. If you take constant load, yeah. I hope Sheikh it is clear. Yeah. Okay. So if Q is constant, will 3 element case and 30 element case will case the same results? Sure. Sure. It cannot be tell sure. The thing that if you have analytical solution, I cannot tell exactly equal. You have analytical solution and your formulation, and then analytical result, your formulation, then Abacus, 3 elements. So let's say this is your 3 elements. Then Abacus, 30 elements. So this will match. These two things will match. these two things will match. So what is going to happen that, so when you are increasing the number of elements, analytical result, you will come closer to analytical result. So this may not match. These two things, analytical result and abacus result, may not match. So when you increase the number of elements, it will match. So it will come more closer to analytical result. This may come less closer to analytical result. So when you increase from 3 to 30, 3, when you divide into 3 elements, it may not close to analytical solution, but you divide into 30 elements, it will come closer, much closer to analytical solution. Is it clear, Abraham? Then we will do a very simple problem. I hope Galerkin method, I found some of you have doubt in the discussion forum that I may that I did not read it completely. So I am going through here just before the class, and I found out that some of the hit. So we will do a simple Galerkin method problem. I hope that all of you went through that one. Just do this problem. You just take only one polynomial function. So the differential equation is dy by dx. It is a simple problem. Dy by dx minus y minus 4x equal to 0. The boundary conditions are y at x equal to 0 equal to 0. So just consider a polynomial of degree 1. So that means y you can consider as a0 plus a1 x. So this you will get only y is equal to a1 x, a2 will be equal to 0. So phi, the function is equal to x. Yeah, just solve by using Galerkin method. Okay. So you have 7 minutes. You have just takes only 7 minutes to solve the problem and 5 minutes to upload it. It's a very simple problem. Actually. That is why I kept it very simple. Upload by 12:13. Polynomial of degree 1. dy by dx minus y minus 4x equal to 0. Y is equal to x 0 0. So residual will be equal to dy by dx minus y minus 4x. Approximate solution is equal to y is equal to a1x. Just use the Galerkin method. So it's a very simple problem actually. So sorry, it is tutorial 17. I just forget the number. It is 17. If you have any doubt, you can ask. I am here only. But this problem is very simple actually. It's less complicated than the problem which we completed in the video, in the last recording. The domain is over. So the domain is actually 0 to 1. You can take 0 to 1. That I forgot to mention. Domain you take it as 0 to 1. Even if you can assume something, since I forgot, even if you assume something, no problem. The domain is x is varying from 0 to 1. That I forgot to mention. So even if you assume some value for domain, either 0 to 10 or something, that is still okay, no problem. No issues, no issues. You can assume also. So domain is 0 to 1.